exam next week. We still have, and it's going to be on Wednesday. So we have our Monday that we're going to use to kind of review. There's a practice exam. May not be enabled. I got to remind myself to do that and make sure that you guys can see it on D2L. But there'll be an outline, same as before, just kind of a list of everything we've gone over. Not guaranteed 100% comprehensive, but I tried to make it comprehensive. That shows everything we've covered. This is pretty much all the stuff we've covered since, yeah, I guess since, well, this is not even all the stuff we've covered since the last exam. But this is the stuff we've covered most recently, so photoelectron spectroscopy. We didn't have that on this quiz, but you can probably, you'll see a question about photoelectron spectroscopy on the exam. So that would include, identifying what elements you're seeing, what the peaks mean, how many electrons, things like that. So shell model, this is all about expanding our shell model into subshells. And that led to electron configurations. And then we went over kind of how the periodic table is set up again. That's, the reason it's split like this has a lot to do with these subshells. Then we went over the quantum mechanical model. Now there's a lot of, I think, some built-in frustration in this because we can't really explain it too deeply. But the big takeaways are, one, Heisenberg's uncertainty principle. Because we're treating electrons like both particles and waves, we have limitations now in how to describe an electron and how to describe where it is, what it's doing, how much energy it has. So Heisenberg's uncertainty principle, make sure you understand kind of, in general, what that means, that you can't know both the energy and position of an electron well. There's going to be uncertainty in that, in understanding those things. What is Schrodinger's equation? So you don't need to know what it is exactly, but what does it do? It's an equation developed to understand the motions of electrons around an atom. And it's complicated, more than that we can cover in this class. But from the Schrodinger equation, if we input certain parameters, these parameters called quantum numbers, we can get different solutions of the Schrodinger's equation. These solutions are called wave functions. And these wave functions are used to create this picture, this model of where we can find the electrons called orbitals. And so how do you visualize orbitals? These are regions of space around the atom where you're likely to find the electron. So remember, the electron is not a thing anymore, not a point in space. It's kind of smeared over an area of space. And that's where they're located. That's where these electrons are kind of smeared in these regions called the orbitals. So the last lecture, we kind of took a look at what the shapes of the orbitals were, what the quantum numbers did for those, what they meant. So hopefully that still makes sense. And we started talking about electron spin. This is the fourth quantum number. So it's this quantum number is not related to the orbital. It's instead part of the electron itself. And I mistakenly said something about it, but I'll correct myself when we get to it. And so we're going to continue from there. We're going to talk a little bit more about electron configurations. There's some more interesting ones that we haven't talked about yet, especially in transition metals. And that'll be it for what's on the exam next week. So, there's not much left to cover. Not much new stuff. We'll probably get to a little bit of covalent bonding today if we have time. And that'll be kind of where the next step takes us. That won't be in the exam. So you'll probably forget about what we talked about today, and I'll have to remind you next time. But that's the kind of idea. So quantum numbers. Learn the rules for what's allowed, what's not allowed. All right. What are the values of quantum numbers? What do they mean? So N is the shell, the energy level. L is the subshell, or the type of orbital, SPD. It governs the shape. And then the M sub L, the only thing we really care about M sub L is how many M sub Ls there are. So if there are 3 M sub Ls, that means there are 3 p orbitals. That's kind of what it means. Okay? And they govern the orientation, which particular kind of p orbital. Is it the z-axis one, the y-axis one, or the x-axis one? Whatever, however you define those. We went through these, so I'm going to skip through these, So trying to identify what the orbitals are by their shape. This is a d orbital, then it's in the third shell, so it's a 3d orbital. That is a p orbital. That is one of the unique d orbitals, but that is a d orbital. So there it is, 3p, and that's a 4d. All right, so we went over all this. This is just up to the third shell. It just keeps going. So energy level 4 will have a set of S, P, D, and F, and it'll keep going. And you might be thinking, well, are there any orbitals past F? Yeah, there are. They're not standard, and you can put electrons in those orbitals when you excite them. But as far as ground state, we don't see them. All right, they're not part of like the normal electron configuration. So this was kind of tying in what we learned in Chem Activity 7A, or 7B, I guess, when we did energy levels of hydrogen. So we calculated these energy levels, N1, N2, N3, and then N4, and it keeps going, but it gets closer and closer as you go up in energy. And we looked at the transitions between these energy levels that corresponds to the photon that is emitted, and hydrogen fit perfectly. Like, so the wavelengths we calculated for the transitions from 4 to 2, that gave us the teal photon, and that wavelength fit the measured photon perfectly. And the idea here is, well, what happened to the subshells? These are just the shells. If energy level 2 has an S and P subshell, why don't we see two different energy levels for 2? Well, for hydrogen, which has 1 electron, the S and the P subshell are degenerate. They're the same energy. So this energy level here is actually all the S and the P's all together. They're all the same energy, so we don't see any difference between them. Once we get to multi-electron atoms, anything beyond hydrogen, the subshell energies start splitting. Like, so this is now different from this, and these are different. So it gets a little more complicated when we get to polyelectronic atoms, or multi-electronic atoms, however you want to talk it, however you want to say it. And really the main reason is shielding. So some electrons, an electron in a 2s versus a 2p orbital will shield electrons, in differently. So if you remember though, you don't have to remember them, but in some of the slides we showed you this psi squared, the probability of finding the electron, and here was the radius, and we saw these graphs that kind of did like this. What this is telling us is, how likely are you to find the electron close to the nucleus? And the closer you can find the electron to the nucleus, the more shielding you can do. The more you can shield electrons that can't get close to the nucleus. And so all of those concerns, cause all this splitting. All of this, so I'm just hand waving here, but the splitting comes from all the different kinds of shielding you can get from different electrons in different subshells. Okay. The other thing we got is that 2 electrons per orbital. So each orbital here, each line, can hold a max of 2 electrons. And that should make sense because when we did our subshell model, we counted 2 electrons in the S block, we counted 6 electrons in the P block. Well, if there are 3 orbitals, 6 electrons, that's 2 electrons each. And it works the same way for the D orbital. So with our subshell model, we counted 10 electrons in the D subshell, or the 10 max electrons in the D subshell. If there are 5 d orbitals per subshell, that's 2 electrons each again. So every orbital holds 2 electrons. We also went over how the electrons fill the orbitals. So electrons want to be in the lowest energy orbitals possible. And so when we learn how to do electron configuration, we start with the lowest energy orbitals first. We start with the 1s, then the 2s, then the 2p, then the 3s, then the 3p. After 3p comes 4s, then the 3d. It's just not written on here. So, but we learned how to do that. And there's a name for that. It's called the Aufbau. I forgot the rest of it. But it's a German word, and it means from the bottom up, I believe. I don't know any German. That's kind of what I remember being taught. But we go from the bottom up, all right? So then we got to electron spin. There are properties of an electron that were discovered from this experiment. So again, this experiment was we were shooting silver atoms through a really strong magnetic field. And if it's a neutral atom with nothing, you don't know anything else, just a neutral atom, we would expect it to go straight through. But this weird silver atom that was neutral, half of the atoms went up, half of the atoms went down. And the reason for that is this silver atom had a single electron in it. Well, silver normally has 47 electrons. But one of those 47 electrons was unpaired. It was kind of by itself in an orbital by itself. And that's unpaired electron, that electron that was in an orbital by itself. Every other electron had a second electron in the orbital. It was sharing an orbital with a second electron. But one of them was by itself. And for this to make sense, that single electron that was by itself must have had this spin component to it that caused it to either deflect up or down. And so this is where we get this idea of, I keep getting shocked, electrons having a spin component, spin up or spin down. It's kind of random which one they are. So that's why half of them went up, half of them went down. And this spin component actually, electrons are negatively charged. Somehow they have this spin component that creates a magnetic field. When you move an electric charge, you generate a magnetic field. When electricity flows through a wire, there is a magnetic field associated with that because the electricity is flowing. Same here. So this is generating some kind of magnetic field, and that electron's magnetic field interacts with this magnetic field to cause it to either go up or down. It's really, really strange how this works. I get shocked again. God, it's really bad. So let me pull up a video that I kind of, not perfect, but it helps. It's on the Tutte Quantique website. There it is, Quantum 101. Spin. So the idea here is they're going to have a strong magnetic field, and they have bar magnets that they're sending through. And these bar magnets are oriented south and north. And if you send it through this strong magnetic field, it will then magnetic. The magnet is flipped sideways. If it's flipped the other direction, it will rotate downwards. That's kind of what happens. This is classical mechanics. We do this at our level of the school. So now, you do the same thing with atoms. Atoms that have a single unpaired electron, kind of like silver. You don't get this spread of, electrons are acting like environment. Quantized. Anyway, that's the best I can show you. It's really weird. Now, let me talk about the side effects. So what does that do for us, knowing the spin? Well, first of all, and we're going to use arrows to represent electrons. So when you draw an electron in an orbital or in an energy level, the arrow is either going to be pointed upwards, and so we're representing an electron spin up, or it's going to be pointed downwards. That's an electron that spin down. You don't have to use half arrows. You can use regular arrows too. That's fine too. But half arrows is kind of what we're used to in chemistry. And the quantum number, the value associated with this spin up or spin down for an electron, and I'm not going to explain why, but it's just plus 1/2 or minus 1/2. It makes a difference when you compare it to other things, which we're not going to, but nuclei have spin too. So the protons and neutrons inside the nucleus have their own spin, which can be a fraction or it can be a whole number. It's complicated. So electrons have this plus 1/2 or minus 1/2 spin. Okay. Now, so what does that do for us? Like, why do we care at this level? So there is something called magnetic moment that you can measure, and that is the strength of an attraction to a magnetic field. So if you have a sample inside of a glass tube and it's attached to a balance, you can weigh its, you can get its mass. So ignore this magnet for a second. It's pulling down, the same as if you would put the sample on top of the plate or something like that in a lab balance. You can weigh its mass. Well, then if you introduce that sample to a strong magnetic field, depending on what kind of sample it is, if it's a paramagnetic sample, we'll talk about that, it will be attracted to the magnetic field. And so if it's attracted to this magnetic field, it'll pull downwards more strongly, and you'll see an increase in the mass value. So it doesn't have a higher mass, it's just you're getting a higher number because of the attraction of the magnetic field. It could also be the opposite, in which it's diamagnetic. And in a diamagnetic sample, we sometimes think of it as having no effect by a magnetic field, or even just slightly repelled. So how do you get this? Well, anything that has unpaired electrons inside, any unpaired electrons, you'll have a paramagnetic sample. If you have a material that has just all electrons paired up, so in every orbital, if there's an electron in it, there's a spin up and a spin down, those are diamagnetic. So you have to have an orbital somewhere in the sample that has just one electron in it to be paramagnetic. So before we do that, let's do this. I pulled up a YouTube video. So this one is interesting because it shows these diamagnetism versus paramagnetism. And before I start, there's a third one called ferromagnetism, which we're not going to talk about, but you guys know ferromagnetism. That's the regular magnet. So when you have something that will attract pieces of metal, that's what a ferromagnet is, and he'll describe what it is, but we're not going to worry about it too much.
You might not think of water as being magnetic, but it is, and so are graphite, aluminum, and glass. This is a new and different category of magnetism called either para or diamagnetism, and it's different from the magnetism that you're used to. You're probably already familiar with ferromagnetism. Ferro means iron. An unmagnetized piece of iron, or nickel, or cobalt, becomes a magnet in the presence of a magnetic field. The effect is strong and lasts even after the magnet is removed. Paramagnetism is a similar effect, except that it's much weaker and temporary. Aluminum is a good example of a paramagnet. And so is oxygen, which is attracted to magnets. Here, I have a few milliliters of liquid oxygen, which sticks to the magnet. I'll explain why later. Gadolinium oxide and cupric sulfate are good examples of paramagnetic substances. Cupric sulfate is a salt that can be picked up by a magnet. Diamagnetic materials are exactly the opposite of paramagnetic. They are always repulsed. They would rather die than be in a magnetic field. An important example of a diamagnetic material is graphite. This specially made pyrolytic graphite is repelled by a magnetic field. Don't be confused. This is not static electricity or eddy currents. Graphite is repelled by a magnet, always, both by the north and south end. Pyrolytic graphite is a grown crystal of flat carbon layers which maximizes the diamagnetic effect. Of course, the best diamagnets are superconductors, which at low temperatures provide exact opposite repulsion to whatever magnetic field is present when they're chilled. They are perfect diamagnets. The most famous and powerful diamagnetic is bismuth, element number 83 on the periodic table. The bismuth-powered boat sails toward the weaker magnetic fields. One way to check whether an object is diamagnetic or paramagnetic is to see how it aligns itself in a magnetic field. Diamagnetic objects like glass will rotate to avoid magnets. Here, we see that the glass is diamagnetic because it twists to get to the weaker magnetic field. But aluminum rotates into the field, typical of a parallel paramagnet. On the periodic table, we see that aluminum has 3 valence electrons. So what does it take to understand what it means for something to be a paramagnet or a diamagnet? You have to know what the electrons are doing.
All right, let's stop it there. So this, I just wanted to show you kind of the materials and what that does for us in real life. So let's try this ourselves. So in Chem Activity 11, page 201, 203. I think we haven't done this yet. Maybe we have. Let me double check. 201 and 203, questions 1 through 11. Oh, no, we haven't done it. Okay. it's time to talk. I can't remember when we started this, but I think some people have gotten through all of it. Some of you haven't, but let's just talk about these right now. So the arrows, these are all electrons, and the arrow pointing up, spin up, the arrow pointing down, spin down. What generalizations can you make about two electrons in a filled S subshell? So all of these, this one and this one, there's one up and one down, always. All right, so we know that already. In an orbital, you have to have one spin up and one spin down. You can't have both up and both down. This is a okay. Let's leave it at that for a second. So, why is the situation of equal numbers of spin up and spin down electrons referred to as all the electrons being paired? I mean, it's kind of self-explanatory in this case. These are all paired. This is paired, and that's it. And that's because everything has a pair. You don't have any unpaired electrons. So that is an unpaired electron. That is an unpaired electron. That is an unpaired electron. All right. So 7. This is the big deal. We can translate this into predictions. Predict the results of a Stern-Gerlach experiment on a beam of atoms. So for each of these materials, will they just pass right through, or will they deflect just like silver did? And if you look at, so we're doing lithium, beryllium, boron, and carbon. These are the last 3 plus carbon. So lithium has an unpaired electron in it. And so the fact that it has this unpaired electron, it could be spin up. In this case, it's spin up, but it also could be spin down. It's pretty random which unpaired electron you'll have. So half of the atoms will be deflected up, half of them will be deflected down, just like silver did. Beryllium won't do the same thing. So beryllium, every electron is paired, and so when you try to shoot it through a strong magnetic field, nothing will happen to it. It'll just go straight through. But for boron, you've got an unpaired electron. And suddenly, just like lithium, you're going to have either the spin up or spin down case, and so you'll have deflections up or down based on for boron. Now for carbon, there's no electron configuration up for carbon, but hopefully you can realize that carbon is one more electron than boron is. So for carbon, you'll have the 1s, you'll have the 2s, and you'll have the 2p, and it'll have 6 total electrons according to the periodic table. So 1, 2, 3, 4, and then 5. And according to Hund's rule, we do 1 electron in each degenerate orbital, degenerate meaning same energy orbital. These 3 2p orbitals are the same energy before we pair them up. So this will have 2 unpaired electrons. So yeah, these will deflect just like just like boron did and just like lithium did. In fact, it should deflect more, or it could deflect more because of the fact that there's 2 unpaired electrons. All right, we have the potential to have a stronger deflection. So then we get to real data. And what you're seeing here are magnetic moment measurements. This is basically how these materials interact with the magnetic field. Are they attracted to the magnetic field or not? And this is a measure of their attraction to the magnetic field. So hydrogen is attracted, whereas helium is not. So you saw in that video, they're slightly repelled. Diamagnetic materials are slightly repelled. So while paramagnetism is a weak attraction, the diamagnetic repulsion is even weaker. So that's why sometimes we don't even say that they repel. There's no attraction at all. So other than helium, which other element has all of its electrons paired in table 1? That was beryllium. And based on the table in data in table 1, individually rank the following atoms in terms of number of unpaired electron. So there's 1 unpaired electron in this hydrogen. There's no unpaired electrons in helium. There's 1 unpaired electron in boron. There's 2 unpaired electrons in carbon. And then skip nitrogen, do oxygen and neon. So for oxygen, no, we don't. Why are we? No, we're not skipping nitrogen. So for nitrogen, there's 3 unpaired electrons. For oxygen, there's 2. So this is carbon. If I turn this into nitrogen, there's 1 more unpaired electron. So there's going to be 3 unpaired electrons. If I do oxygen, it's got 8 electrons, so the 8th one would go there. Back down to 2. We're not doing fluorine, but when we get to neon, that's 10 total electrons. And you can see that for neon, there's going to be no unpaired electrons again. So, I didn't write them down, but 1, 0, 1, 2, 3, 2, 0. For some reason, fluorine's not on here. So, make a diagram for carbon similar to those in Model 1 that show why carbon is paramagnetic. When we did that, we can do it again. There's carbon. And explain how your diagram is consistent with your answer in Table 1. Well, it's paramagnetic. There you go. Unpaired electrons. Would you revise? So if you use my answer, then I know I'm not going to revise it. If you have your own, now that you see why, maybe you would revise your answer. And then let's see, it's 11. So make a diagram for nitrogen that is consistent, and then, okay, so 11, nitrogen looks like this. And yeah, it's got 3 unpaired electrons. And this is really the reason why the magnetic moment for nitrogen is just so high. It's so big because of the fact that it's got 3 unpaired electrons. When you drop back down, when you get to oxygen, there's only 2 unpaired electrons, and so the magnetic moment drops again. All right, so this concept of electron spin is a big deal. It has a real-world effect on materials. In the video, they showed oxygen, liquid oxygen, being attracted to a magnetic field. I'm going to warn you that it's not because of this. Because this oxygen is atomic oxygen, 1 single oxygen atom. So atomic oxygen is paramagnetic. But the liquid oxygen they showed in the video was O2, the molecule O2. We'll eventually get to looking at electrons and their spins and how they work in molecules, but we haven't quite gotten to that level yet. So I'll tell you why it's different. So nitrogen, the atomic nitrogen, we predicted to be paramagnetic, the most paramagnetic substance on here. But nitrogen, the gas, N2, is diamagnetic. It's not attracted to a magnetic field at all. So when you start making molecules out of these atoms, things change quite a bit too. So we'll get to that. We're not there yet. We're doing atoms still. But hopefully that makes sense. In case you were curious on what paramagnetism is compared to regular magnetism, which is we call ferromagnetism, I think there's a video that kind of shows it okay. So in order to have magnetism, you need these unpaired electrons. Okay? Any kind of magnetism, whether it's ferromagnetic or paramagnetic. So here is a sample of some material that has these unpaired electrons. There's an atom with an unpaired electron that actually can point in any direction. And here's a material, a whole bunch of atoms near each other, and these electrons are all pointing in different directions. This is a paramagnetic material. And the reason why, when you put this in a magnetic field, the external magnetic field will cause all of these spins to align with that external magnetic field. So suddenly it's so there's the magnetic field, they all align, and so it's attractive. It interacts with that magnetic field. And then when you get rid of the magnetic field, they're all kind of random again. That's a paramagnetic material. But in some solids, they interact. And if the temperature is low enough, so the way you think about temperature is, this is not what we're going to get an exam or anything, but temperature is kind of energy, it provides a lot of energy and motion. The higher the temperature, the more vibration, the more energy it'll have. The lower the temperature, the more likely individual spins will influence each other, and they'll self-align. And that's when you get this paramagnetic material. So in case you're curious, there's this temperature called the Curie temperature. If you're below the Curie temperature, your material is going to be paramagnetic. It's automatically magnetic. So like the magnifier is going to be a magnet. Those are paramagnetic materials. If you were to suddenly take that paramagnetic material, you would lose the magnet. Heat it up a lot. You would lose its magnetism. You go above the Curie temperature. All the spins are now in. So that's kind of what it is. We're not going to get that into this at all. But like magnetism is fascinating to me, so it's hard to understand sometimes. But that's where that comes from. Electron spins. I mistakenly talked about NMR, nuclear magnetic resonance, and MRI. It is related to spins, but it's not the electron spins, it's the nuclear spins. So I did make that mistake last time. But it's related, so it's all it's all related. Anyway, let's get back to this. Any questions on unpaired electrons, stuff like that? We'll come back to it. We'll start to look at unpaired electrons in molecules eventually. But we looked at carbon. That's carbon right on the left. Which one of these is correct for nitrogen? I'm just going to show you the answer because we kind of looked through that. It's still on the board right there. A. So which of the following is paramagnetic? So you've got three options there, or more than one, or none. So to be paramagnetic, at least one unpaired electron. As long as there's one, it's paramagnetic. So I would recommend, let's see what people say. Oh, we got guesses all over the place. B, C, or two or more. Or two, exactly. So the way I would do it, and it is B, is I would start with just electron configuration, just to make things quick. So if you look at the electron configuration for calcium, it's argon core. And everything in here is going to be paired up. Everything's full. So ignore that, and now look at the rest of it. It's 4s2. That's calcium. Well, s orbitals come in sets of 1. That's it. And there's 2 electrons in here. Those are paired up. So that is diamagnetic. The chlorine is neon, then 3s2, 3p5. So that is paired up, but this, 1, 2, 3 p orbitals, 1, 2, 3, 4, and 5. There's one unpaired electron there. So the chlorine is paramagnetic. But chloride is the same, except it's got one extra electron. And so that one extra electron now means there's no unpaired electrons. So chloride is diamagnetic. Only chlorine atom neutral is paramagnetic. Okay? Okay, we went over Hund's rule. Hund's rule, 1 electron per orbital in degenerate orbitals before you pair them up. So all the p orbitals are degenerate with each other. So you do 1, 2, 3 like that. If you had 3, not 1, 2, 3 like that. Okay, we've done this. We've seen this slide. The reason for Hund's rule is to minimize electron-electron repulsion. You don't want 2 electrons sharing the same orbital if they could be in separate orbitals. They want to be they want to be separate. They don't An electron negative charge doesn't like the negative charge on another electron. The Pauli exclusion principle, the short version of it is that electrons must have opposite spins when you put them in the same orbital. We'll talk, well, the full version of the Pauli exclusion principle, I feel like we're going to get to it, but I'm going to spoil it here. The full version of the Pauli exclusion principle is that no two electrons in an atom can share the same set of quantum numbers. So basically, you can take any electron in an atom, like this one, and assign the 4 quantum numbers to it. Right? So this is in shell 3. It's in a p orbital, so L is 1. The m sub L value, all right, it doesn't really matter which one it is. It's either the -1, the 0, or the +1, who knows. Let's just call it the +1, it doesn't matter. And then it's spin up, m sub s, that's the spin value, +1/2. Every electron must have a unique set of quantum numbers. So no other electron can have this exact set of quantum numbers. That's really what the Pauli exclusion principle states. Think of this as like an address, these 4 quantum numbers. They all have to have a unique address. Okay. So there it is. It was the next slide. So each electron has its own unique address. And so why spin down? Well, that gives it a -1/2 spin, which is a slightly different address. Every electron has to have its own unique set of 4 quantum numbers. Okay. Now, these orbital diagrams, we went over this. And we talked about which element this is. This is fluorine. Orbital diagrams show, like this, what the spins are and where they are in which particular orbitals. You can do it on a vertical axis with energy, or you can just do it in a row like this. Like this, it's clear that this is low energy, this is next, and this is the highest energy. When you put the boxes together like this, it's saying that these are all the same energy. Okay? So just know the difference between electron configuration and orbital diagrams. A partial orbital diagram would be just the valence orbitals. Right? That's all. So you'll see that too. And so yeah, that's a partial orbital diagram right here on the left. Okay. So we talked about some of these conclusions already. I think I'm going to go through them quickly. Yeah. So the last two, I think, are the important points. And I did mention them last time, but let's go over them again just to make sure. When you're talking about valence electrons, so before we kind of just casually said, look at the group number it's in, that's how many valence electrons they have. Oxygen has 6 valence electrons because it's in group 6. And for the most part that works. For main group elements, that works really well. And even when you talk about electron configuration, so the electron configuration of bromine is argon core, 4s2, 3d10, 4p5. We would only count the outer shell, the shell 4, for its valence electrons. Right? So bromine has 7 valence electrons. So for main group elements, you just count the outermost shell. That's it. Now for transition metals, like nickel, the electron configuration for nickel is argon 4s2. And again, I'm just looking at the previous noble gas, and then I start in row 4. That's the s block, 4s2, and then this is the 3d block. 1, 2, 3, 4, 5, 6, 7, 8. 4s2, 3d8. Transition metals are a little special. When we look at the valence electrons, we are going to include the 3d subshell. So all of these are included in the valence count. So this has 10 valence electrons. The reason that we do this is because the 3d energy and the 4s energy are really close together. And so all of these electrons would be able to interact with the outside world. Whereas for bromine, honestly, if I'm doing it correctly with energy, the 3D is actually lower in energy than the 4s in this case. So really the 4s and the 4p are the highest energy subshells in this case. So that's why we ignore the 3D when we get to the main group elements, okay? So just keep that in mind when you're counting valence electrons. We do the valence electron count for transition metals a little differently. Okay. And this would include F block elements as well. So include the F block if you're, so for uranium, if you're doing the valence electrons for uranium, you would count the F block elements too, or F block subshell. Okay. So diagrams, hopefully this isn't too tasking, but an orbital diagram for iron. An easy way to start this is to start with the electron configuration. So for iron, the electron configuration is argon. Actually, let's do the whole thing. 1s2, 2s2, 2p6, 3s2, 3p6. And I'm just kind of scanning the periodic table just to come up with these. After 3s is the 4s, and it's filled, and then after 4s is the 3d. And we count over 1, 2, 3, 4, 5, 6. There we go, that's the electron configuration. The diagram, you just kind of rewrite this using blocks that represent orbitals. So here's the 1s, here's the 2s, here's the 2p's. Alright, this has 2 electrons in it, this has 2 electrons in it, this has 1, 2, 3, 4, 5, 6. Next is 3s. Next is 3p. I'm not drawing it with Hund's rule in mind, but it works out anyway. Next is the 4s. And then finally, 3d. And remember there's 5 d orbitals. So there should be 5 boxes. And it's filled with 6 electrons. So 1, 2, 3, 4, 5, and then we can now finally double up, pair up, 6. That is the orbital diagram, the full one for iron. The condensed orbital diagram would be just this part. You could do this. You could, to be clear, it's an argon core, and then the rest of that stuff. Okay. So, orbital diagrams, almost the same as condensed or electron configurations. Just slightly more information, that's all. There we go. I'm pretty sure the reason that we do full arrows on PowerPoint is that it's hard to find half arrows in font packs. But otherwise we would do half arrows like this. It's fine, you could do full arrows if that's what you're comfortable with. Okay, I feel like we did this one last time. Yeah. So, which one has more unpaired electrons? To answer this, you have to do an orbital diagram. And you'll find out that manganese has the most. Why? So manganese has an argon core. And then here's the 3D. And if you count over, so the S is full. And then 1, 2, 3, 4, 5 for manganese. So 1, 2, 3, 4, 5. 5 unpaired electrons. Whereas vanadium only has 3 unpaired electrons. If you look at the electron configuration. And iron has 4 unpaired electrons. There's 6 electrons in here, but one of them is paired up. So 4 unpaired electrons for iron. So manganese has the most unpaired electrons. What does that do for us again? It's got the highest magnetic moment, the strongest interaction with a magnetic field. All right, they're all paramagnetic though. Every one of these is paramagnetic because every one of these has at least one unpaired electron in their orbital diagram. That has 5. This has 4. Vanadium has 3 of them. So they're all paramagnetic. Okay, so let's talk about some more unusual electron configurations. So I think, yeah, this is going to get us to do some work. But when you do a transition metal electron configuration, you fill the 4s first and then the 3d. We've seen this already. After they are filled, so once you get to, for instance, like bromine, even though we fill them like this, I do 4s, and then I fill 3d, then I do 4p. Technically, once the 3d is filled, we start filling the 4p. In terms of energy, this is actually lower in energy than the 4s. Just to keep that in mind. That's, even though I write it like this, sometimes in textbooks you'll see the 3d before the 4s, and it's because it's lower in energy. Now, the other thing, when you're filling transition metals, we know how to do that. But if you're making ions out of them, this is where it gets a little tricky. The 4s and the 3d subshells are really close in energy. And even though the 3d is a little bit higher, when we remove electrons, the orbital subshells rearrange themselves a little bit. And after electrons are removed, after we make zinc, for instance, into a cation, what will end up happening is the 3d will be lower in energy than the 4s. And so, as a result, what we basically are doing is, when we make a cation out of any of these transition metals, we're going to remove the s electrons first. All right, almost always. Not every time, but usually we're going to be removing the s electrons first. So, when we make zinc 2+ out of zinc, we're not going to remove 2 electrons from the d. We're going to remove 2 electrons from the s instead. And so the electron configuration of zinc ion is argon 3d10. You might think that's a little strange, but it actually explains a lot of the weirdness of transition metals. So one of the things about transition metals that make them difficult is they have multiple ions that they can form. This actually explains some of those things. So I think we're going to get into, so let's try these exercises and see if they make sense. CTQ 22, exercises 1 through 3 on page 212. Oh yeah, this big long thing. Okay.
What page is that?
Page 212.
Oh, yes.
So the first couple in the block should be normal, like what you're used to seeing. It's the ones that lower down that are going to be the trickier ones. Yep. Yeah. And the noble gas electron configuration, that's the same as the condensed electron configuration. literally just write the noble gas bracket. That's enough. That's fine. No problem. If you're getting the same answer over and over, it's not a mistake. Feel free to write your own shorthand for whatever you need. the reason is because after everything's settles, after you've removed electrons, the 3d orbitals are actually going to be slightly lower in energy than the 4s, even though normally they're higher. Right? So when we do the neutral atoms, right, we do 4s and then 3d because the 3d is a little bit higher in energy. But after we've ionized them, the energy levels of the different subshells change. And it just happens that the 3d becomes slightly lower, which is why we remove the 4s electrons first.
Oh, I think I just got mixed up. Like, for some reason I thought 3D or D started in row 4 instead of 3. I forgot that starts in 3.
Oh, okay.
Yeah.
Okay. Okay, and then finally, it's going so well. Okay, I think you've puzzled over some of this, hopefully enough that you're like, you know what you know, you don't know. The first 7 elements are all the same. 1s2, 2s2, 2p6, okay? They all look like neon. When you get to argon, argon looks like argon. Calcium 2+ looks like argon. But when you get to scandium 2+, this is where you get to the transition metals. And it's just, you're going to have to remember as a rule that the transition metals, when you ionize them, turn them into cations, they're going to lose the 4s, the s electrons first, whether it's in 4s or 5, like what's the next row down. They're going to remove their s electrons first. And the reason for that is when they're neutral, the 3d subshell is higher energy. And, you know, it makes sense that, if you remove electrons, you're going to remove them from the 3d. They're higher in energy. But honestly, what happens is after you make the ion, when you make Fe2+, the subshell energies actually change, and the 4s is actually going to be higher than the 3d at that point. So they'll rearrange anyway, and all of those electrons will go into the 3d. So ultimately what happens is that the 4s is what loses the electrons. So we go from neutral iron here, where it has the 2 electrons in the 4s. When we make Fe2+, those electrons are gone now. And then when we go to Fe3+, we don't have any more s electrons. So where does the electrons come from? The d subshell. So here is the first clue as to where you get these multiple charges from. A lot of these transition metals have a +2 charge because of that s subshell. Now, where do the rest of those charges come from? I think I mentioned it once before, but having a half-filled subshell sometimes is very advantageous. And so losing one more electron gives a half-filled 3D shell. This is why a common ion of iron is also iron 3. So here's scandium 2+. We know that exists. What other ion of scandium probably exists? Well, what if we remove the 3D electron? So a scandium 3+ probably is a very common ion, because then you're basically getting 1s2, 2s2, 3, sorry, skipping one, 2p6, 3s2, 3p6. Right, and so now that single d electron is gone, We've gone from scandium 2 plus to scandium 3 plus. We lost that last d electron. And that's why the main ions for scandium are scandium 2 plus and scandium 3 plus, and that's it. That's why we have these multiple ions for transition metals, because you get these different patterns. What about titanium? Well, titanium 2 plus is one of the ions. What do you think the other ion is? So what else do we have to lose in the d shell? We've got 2 electrons we can lose. So having a half-filled shell and an empty shell, these are like the common scenarios we'll see. So what if we emptied out the d shell?
Is it 3 plus?
Well, if it's 2 plus already, and if we took away both of these electrons, it would be titanium 4 plus now. So titanium 4 plus is the other common ion for titanium. All right, so now it's got an empty d shell, just like scandium 3 plus does. So there's more to it than this, but these are a lot of the reasons why these transition metals have these multiple charges. Can you guys predict vanadium's charges? So 2 plus is one of them, if we remove the s electrons. What would maybe a charge of vanadium also be?
5 plus?
5 plus, yeah, that exists. There's others, so it's a little more complicated than what we're talking about here, but this is one picture into that, into the reasoning why we have all these multiple charges. I think maybe you can see why zinc is always 2 plus, because if we lose the 2 electrons for zinc, those are the 2 s electrons, and then it's got a filled d shell, which is actually pretty good for zinc. Cadmium is the same way. Why is silver only +1? That's a little more difficult. So why would silver only be +1? So, like, that's the only ion for silver.
Because the last electron from the s orbital will go to the d orbital.
Exactly. Yeah, you got it right. So silver, regular silver is argon core 4s2 3d9. That's regular silver. So what I'm telling you is silver is only makes silver plus. Well, okay, where would it come from? Well, normally it's a transition metal. It comes from the s. Well, now the energies have kind of rearranged themselves. This may not be lower in energy than this anymore. In fact, it's not. It's actually the other way around. So it's really this. So why is that electron still hanging around in the 4s? It's actually going over there. And that's what silver's electron configuration is. You've got an empty s shell, subshell, and a filled d shell, which is pretty good for it. And that's why silver is only +1. So we started out with memorizing these exceptions, or not memorizing, but realizing they exist, and we're starting to be able to explain them just from these concepts of electron configuration. So I think exercises 1 through 3. Yeah. I'm going to leave it up to you to come up with your own explanation for how this works, 1 and 2. But for 3, what is that element? Anybody get to that? So xenon, which is starts in row 5, or ends in row 5. So 6s2, 4f14, 5d10. So we're basically filling up the F shell, filling up the D shell, and that's it. Looks like this element to me. Mercury. Hg. Forgot what Mercury's old name is. Hydrargium, something like that. Anyway, that's why it's got this weird symbol. Anyway. All right. Questions on the electron configuration of transition metal ions. So we've done electron configurations for neutral atoms. We've done electron configurations for regular ions, like the main group ions. And now we've got these specialized electron configurations for transition metals. Now, if you're worried on an exam, I'm not really interested in quizzing you or on speculative stuff. But in general, for a transition metal, those electrons will come out of the 4s, the s shell subshell first. You have to know that. So when I asked you to write, what is the electron configuration of blank transition metal ion, you should be able to write it. Okay? Okay. So that's it for exam 2 stuff. All right. Beyond this, there's no more. So we'll go over this again on Monday. So don't stress that I'm not going to keep it up, but there is a lot. So one thing we didn't talk about at all was emission spectra, all that stuff. That's going to be on the exam too. But everything else here too. Okay. So we're not going to do too much of this. We don't have much time. What we're going to now do is we're going to switch from atoms to molecules. I think we've studied atoms enough. Let's take what we know about atoms and kind of figure out how to have atoms interact with each other. We understand their electronic structure very well. How do those electrons interact with other atoms to make bonds and stuff? So we're going to start with covalent bonds. That's the most, I guess, what people think of when they think of chemistry. And we'll do Lewis structures. And there's going to be a whole lab devoted to Lewis structures. So if we go over it kind of casually in the lecture, you're going to get a lot of it in the lab. So don't worry. So we're going to have to understand bond order, bond strength, bond length, resonance structures. So this shouldn't be a foreign idea once I explain it, because it has a lot to do with the idea of what an electron really looks like. Electrons in an atom are delocalized, right? We don't say it's here, it's spread out. That's going to be the same idea for a molecule. And that's where resonance structures are going to tie into it. And so you'll see. And then we're going to do something called formal charges. That's just it's not really a charge, it's a tool we're going to use. And electronegativity. So once we get past the Lewis structures and understanding of covalent bond, then we'll get to 3D. So we'll have to understand how a molecule is constructed three-dimensionally, what kind of shape they make, because that actually has a large role in what kind of properties it has. So we'll have to understand something called valence shell electron pair repulsion theory. It sounds like a mouthful, but it boils down to a really simple idea: electrons repel. So once you understand that, it's easier to understand how shapes might take place. We'll go over that. And then once we are masters of the shape, like we know what a molecule looks like in 3D, then we can understand dipole moments. Are there charges on one side of the molecule versus another? Or is it kind of like neutral all around? So we'll get to all that. If we have time, well, actually we're going to have time, we're going to understand how the electrons interact to make the covalent bonds. So we'll start off with just understanding they make covalent bonds and in general how they form. But we're eventually going to tie in the orbital stuff we learned this week, last week, to molecules and how those orbitals interact to make the bond. And the hardest part of this, if we have time, is molecular orbitals. So it's a different theory for bonding. So organic chemists, and probably you guys will like valence bond theory, which is kind of like how atoms connect to other atoms and make covalent bonds. It's a very visual way of thinking about a bond, how a molecule forms. It's very easy to understand once you get the hang of it. Molecular orbital theory is another way of thinking about how a molecule forms. And it's not as visual. Like if you can't think of it as, oh, here's two atoms coming together, they share this. It doesn't work that way. It's more quantum mechanics. It's more of that. And we're not going to get too deep into it. This is kind of an intro to it for 221. You will study it more in 222. You'll need it to understand how to talk about how metals work. Why are metals conductive? You'll need it to understand how semiconductors work. Why are semiconductors sometimes not conductive and then suddenly they can be conductive? All of that is explained using molecular orbital theory. LEDs, how do LEDs work? We're going to go over all of that in 222. So this is the framework for understanding more. All right, I don't want to start anything new. I just kind of want to introduce kind of what we're getting to, so you have kind of a way to think about things, planning ahead. Oh, this is why this is important. I'm excited, hopefully. And if you're not, at least you know what's coming up. All right, let's stop it there. Any questions in any of this? Okay.
A million, probably.
A million?
Yeah.
Take your time.